Okay, question 6. I hope if I have my microphone on. There we go. So question 6. We've got a person standing in the lift, and I don't know why, but the number here isn't correct, so let's just correct that. So that should be reading 590 newtons, just like it says in the question. The vertical contact force acting on the person from the floor of the lift is R, so we've got that coming up and we've got the weight coming down. First part then, A, show that the mass of the person is 60 kilograms. Okay, so what do we know? Well, we know that the weight of the person is equal to the mass times acceleration of free fall. So if I rearrange that, that will tell me that the mass is equal to the weight over G, which is 590 over 9.81, and that comes out as being roughly 60 kilograms. So let's have a look at part B. It's now saying the lift starts from rest. It has a constant upward acceleration of 0.5 meters per second squared, and we have to calculate the magnitude of the contact force R. Okay, so let's have a look. We know, let's do it up here, F is equal to MA, and in here then the F is the resultant force, and the resultant force will take, it's going upwards, is going to equal R minus the weight, which is 590, and that's going to equal the mass of the person, which we just worked out as being 60 kilograms, multiplied by the acceleration, which is 0.5. So the normal contact force has got to overcome the weight and provide the force for the acceleration, which is the 60 times 0.5. And when we plug that into your calculator, so we've got 590 plus 30 equals 620 newtons. And part C, after short periods of acceleration, the lift travels upward at a constant velocity, so i.e. it's not accelerating. Explain why the force R is equal to the weight of the person when the lift travels at a constant velocity, because therefore the resultant or the net force must be 0. And part D, state and explain how the force R changes at the instant the lift starts to decelerate. So if it's going to decelerate, that's the equivalent of having an acceleration downwards. So if we just quick little free body diagram, we've got the weight of the person and the normal contact. Now if the acceleration's downward, therefore the resultant force has to be downward, so therefore R has got to reduce in size so that the weight provides the deceleration. So the weight has to be greater than R for the deceleration.